So what we're going to do now is we're going to walk through the next programming assignment. This is the final programming assignment for the course since we're getting towards the end of it. And the purpose of this third assignment is to deepen your understanding of how to develop asynchronous microservices using a combination of Spring WebFlux and the Project Reactor reactive parallel programming features. In particular, we're going to apply the ParallelFlux reactive type to implement a microservice that provides movie recommendations to clients in parallel by leveraging multiple processor cores. So at long last, we finally got to one of the main goals of the course, which was to show you how to implement a recommendation engine, which is really cool. As we've seen up to this point, the code we're going to write here doesn't really have a fancy schmancy GUI, and it runs as a Spring application, and it's got both an integration main program, so you can start up the services and then run a test program and watch all the magic happen, and it'll also have a whole bunch of unit tests. You'll be graded on the unit tests. Obviously, use this main program and the unit test to see if your solution's working and to debug it if you have problems. There's some resources that could be helpful. There's a couple of overviews of ParallelFlux that appear at these links. And of course, we're going to cover the topics here later today, and that'll be in the playlist here shortly. So this project is packaged up using IntelliJ. It's written in Java. As always, it demonstrates a whole pile of cool WebFlux and Project Reactor features, but you only have to focus on a couple of directories here. So the main ones are client, where you're going to have to add some extra proxies for the client side like you've been doing. And the other is the recommendations module, where you're going to actually implement the microservice that uses the ParallelFlux features in order to be able to give the recommendation engine its parallel boost. In addition, you're going to have to copy over some of the stuff from assignment 2C. We're finally at long last jettisoning. We're getting rid of the mechanisms for movie EX. That's going to be graded as part of assignment 2, so we won't do any more with that. But you do have to have your database microservice implementation, because we're going to tweak it a little bit to add caching and a few more things. Make sure you don't overwrite the tests. Just copy over the parts that provide the solution. So there's a bunch of things you got to modify. As always, please don't change the skeletons. Just fill in the to-do tasks. Don't delete them. And here's what you need to focus on. So we have the recommendations module, and there's a couple of files there. There's ParallelFlux service.java and moviesloader.java. So you have to implement the various to-do tags there. There's also client, where you have to add some support for the proxies using the declarative HTTP interface mechanisms that we've talked about. You've got to add one for the ParallelFlux microservice and a few other things that relate to that. Then there's the database field or database module, where you have to update various fields and methods in database service.java to add support for returning and caching map objects. And this is super duper cool and really fun, and it'll illustrate and deepen some of the things we just talked about in terms of caching. There's a few other little minor things. You got to add support for the factory methods in the client beans.java file, so we can create a ParallelFlux API instance to use as the client-side proxy. And then you have to copy over your solutions in the movies.java file, movie.java file. I might have missed one or two things, but as always, you can see through IntelliJ where your to-dos are. You shouldn't have to have any loops, and there might be a handful of places where you need an if statement or two, just because it's cleaner than trying to put everything into the Procrustean bed of reactive programming for some error handling cases. But in general, please try to use functional programming features and reactive programming operators. Again, as always, you have to pass the tests and address my review comments. Make sure you comment your code or it won't be reviewed. You can get the code in the GitHub repository, which will be put out shortly as soon as we finish up writing the tests. The tests are not done yet, but I wanted to go over this stuff so you'd be ready for it. And of course, I'll record it and put it out. There's a lot of tests. There'll probably be close to 100 tests that run when all is said and done. So make sure that you run those, that you do that by going on task verification check. I think we have fixed the wacky problem that occurred on Mac with the Ultimate Edition of IntelliJ, where it would run the test the first time, but then in subsequent times it would say, test events not received, unless you kind of threw salt over your shoulder and said a Hail Mary or something like that. There's a bunch of weird things you had to do to make that work. I think we fixed that. That's clearly a bug in the Ultimate Edition of IntelliJ, because it worked fine when using the Community Edition for some God knows what reason. As always, there's more to doing things and just passing tests, so make sure you look at the code and respond to the comments that I give you through the review and assessment process. So this assignment is really kind of the capstone, if you will, of all the things we've covered about developing asynchronous microservices using Spring WebFlux and Project Reactor. In particular, its parallel reactive programming features, which we will talk about in a second. There's tons of stuff here. If you really want to see how to implement the recommendation engine, you should take a look at some of the things that I provide you in the skeletons where you don't actually have to implement them yourself. But there's a lot of really, really cool stuff in there. And the actual code isn't too bad, but keeping track of all the different pieces is a little tricky, and you'll have to get used to using parallel fluxes, which can be a little daunting at first because they make you stand on your head to do everything. But make sure you start early, come to class, come to office hours, and/or post questions on the discussion forums so you can get this thing done successfully. So we're now in my IntelliJ project for this particular assignment. And as you can see, there's still a bunch of folders, some of which you have to be concerned with, some of which you don't. So you'll have to be concerned with client, you'll have to be concerned with a little teeny bit of common, a little part of database. The main focus is on recommenders. And then, of course, we've got Eureka and Gateway and testing and timer that provide other services. By the way, by the time all is said and done, we'll have, let's see, we've got the Eureka microservice, which you use but don't implement. We've got the Gateway microservice, which you use but don't implement. We'll have the timer microservice, which you use but don't implement. You'll have the database microservice, which you implement. And you'll have the recommenders ParallelFlux microservice, which you also implement. So there'll be about 5 microservices running around here, which is kind of fun, and it gives you a sense of a bit more scalable style of writing applications than we've looked at so far. So let's start off with the most important part, which is recommenders. So you click down here, and you'll see that there's a whole bunch of stuff here. I'm going to focus on just 2 parts of it. Let's take a look first at Movies Loader. And so the Movies Loader is going to be used by the server beans. And what's going to happen here is when the program starts up, it's going to get a movie map. And that movie map is going to be obtained through this bean, this factory method. And what it's going to do is it's going to say, hey, Movies Loader, load the movies from the database. This, of course, illustrates the fact that the database has to be up and running if you want to do this. There's a run microservices configuration script that will start everything in the right order. If you use it, which you're welcome to do because it's super cool to see how this all works, be aware that it takes a while for these microservices to start up. So I put delays in the run microservices script that gives about 15 seconds between each microservice, because otherwise not everything is up and running by the time things need each other's dependencies. And this is one example of that. So the Movies Loader, load movies from database, is only going to work if the database is up and running and ready to receive requests. So here is load movies from database. And what you're going to do here is you're going to use a helper method from WebUtils to create a URL string, which is going to encode all the information you need to access the database microservice. That includes the protocol, which is HTTP, so that's kind of a no-brainer. The port number, which is going to be the gateway port number. The host address, which will be localhost because we're running it on your laptop. And then you have to put in the path. And you have to make sure that you include the database in the path, because that's how the gateway will route this request to the appropriate microservice, to the database microservice. So you'll have to write that. There's a little helper method to make it easier. This next part is super cool, and it's something I added yesterday. It was really fun doing this. So what we're going to do there is you're going to use another helper method from WebUtils, which is going to take the REST template, which we created up here. So you've got an initialized REST template. It'll take the URL that you make there, and it's going to go ahead and call this helper method, which is going to go to the database and get a map that maps movie titles to cosine vector descriptors for each of the movies. And that also is where the caching comes in. Not the world's most amazing use of caching, but I thought it was kind of fun. So that will go ahead and obtain the map. And it'll basically print out that it succeeded. If it succeeds, if it doesn't succeed, it's probably because the database hasn't started running yet. So just be aware of that. And then it returns the movies map. And that movies map is going to be used over here through something called the base service. So you can see the base service is going to be connected to the movies map. So when everything starts up, that's what's going to get initialized and used. Now, there's a whole bunch of other cool stuff here, which we really won't go into a lot of detail about right now, but there's this base service class. And the reason we have a base service class is we've actually got about a dozen different implementations of the recommendation engine using all types of different concurrency models. So we've got parallel fluxes and concurrent fluxes and parallel streams and sequential streams and a whole boatload of other things. And if you take other courses with me over time, we might get a chance to play around with some of that stuff because it's pretty cool. So this is a generic file that has the definitions of the various operations that are supported on one of these recommendation engine services, such as get me all the movies, search for a movie, do a query and get back results. And then the two most important methods for the purpose of assignment 3, which are different from what we've done before, get recommendations, where you give it a single watched movie and a max count of similarities, and it'll give you back that many movies that match, ranked by similarity. And then another one called get recommendations, where we take the watched movies as a list. And so that'll do the same thing, but you get back a list of movies. Or sorry, you'll give it a list of movies and it'll figure out which ones are similar to that grouping of movies. So let's go down here now and take a look at the ParallelFlux application. I'm still working out some crazy issues with multiply defined beans, which you don't have to worry about because we're not going to put that in the code right now unless we can figure out how to do it. But this is where we start the ParallelFlux application. And that's the microservice. Here's the controller for non-timed operations. And again, you'll see we're still trying to come up with some clever ways to refactor that, which we will eventually figure out, but it doesn't matter. You don't need to do it for this assignment. So the ParallelFlux controller has an application context and an auto-wired service to the ParallelFlux service. And then it's got the various operations that we need. So it has a way to get the ID, which we use for some really cool stuff to keep track of things for timing. And we've got something that Spring Eureka can use, or the Netflix Eureka can use to figure out whether we're still alive. And then we've got the various endpoint handler methods. And they do what they normally do. They're annotated with get mapping or post mapping, annotations with path names, and then we delegate to the service. So we can get all the movies, we can search for all the things that map a given query string, and then we've got the recommendations methods here. And as you can see, nothing particularly interesting or profound there, so I won't spend a lot of time on the controller. I will point this out, though. We also have a timed controller. So I've split the controller up into two parts. We have the part that are the non-timed methods, and then we have the part that are the timed method. And you can see what we do here is we use request mapping in order to have a timed value inserted into the path. So anything that has the word timed in the path will be directed to this controller. And what we do is we have a field that's the non-timed controller. We have an instance of a really cool runtimer class that will then magically direct the calls to the timer service to record how long they take to run. This is absolutely brilliantly cool. I didn't think of this. My friend Mani thought of this. I came up with the idea. He came up with a cool implementation. And here's what it does. So the all movies timed method, which is what happens when you give the timed request from the client side, goes ahead and gets the ID of the controller and then puts the name of this particular path in that ID. So that's going to be used as a key for the timer service to keep track of how long it took for this particular method to run. And then what we go ahead and do is we forward to the actual non-timed version of this method, and this call will record how long it took for that method to run, and it'll go send that over to the timer service, which will then record it in its internal data structure, so that when we're all done, we can go and ask the timer service, how long did the method calls take to run? So it's a really nice way of unobtrusively keeping track of the time. So we have the all movies timed, we have search timed. You can see that they all basically do the same thing. They go ahead and forward to the underlying non-timed method, and then they keep track of how long it took for that to run, and then they send it on to the timer service. So those are what the timer controller stuff does. Again, we provide that for you. Now let's take a look at what you actually have to do. What you have to implement is the ParallelFlux service, and this, of course, is what's going to implement the recommendation engine using ParallelFlux features. So this extends the base service with the return types being fluxes of things called rankings. So what is a ranking? So let's go take a look at what a ranking is. So a ranking is a DTO, which is just a data transfer object. It's used for other things too, but that's one of the things it is. And it keeps track of a movie title and the cosine similarity value. What we're going to do here is when we do the comparisons between a movie or movies that you've watched and the database of movies, we're going to go ahead and figure out, using the cosine similarity index algorithm, which movies have the highest relationship or highest correspondence to the existing movies in the database. And you'll get back a score for each movie title. It'll give you the movie title and then how well it scored. And we sort them, but you can also go and see how close it was. So the higher to 1, the more it's likely to be something that you'd want to watch. The lower scores mean, maybe you don't want to watch it, assuming that you are depending on what you've seen before. So that's what the ranking object is. It's also got a whole bunch of other stuff in it as well that we need in order to do sorting and comparisons and stuff like that. So that's what ranking is. That's what you get back. So get all movies. That's the first thing you have to implement. And what you'll need to do, it's actually really cool. You're going to need to take the movies map and get the key set from that. And the movies map's key set, of course, is a bunch of strings, because that's what you get when you suck in the database containing the movies and their vector cosine similarity vectors. And then you're going to have to convert that into a flux of rankings. And there's a class called the converters class, which is over here in the, let's see, converters class, I think is over in common. There we go. So here's the converters. And these are little helper methods that go back and forth between various representations. So if you've got a collections of movies, then this will convert that into a list of strings. Likewise, if you've got a collection of rankings, we can turn that into a list of the titles. And then there's also a way to take a collection of movie titles and turn that into a list of rankings. And you'll need that to move back and forth between different representations. So be aware of that. So that's get all movies. It's pretty simple. The search method is a bit more interesting. So first of all, we're going to be using parallel fluxes. And what you typically do with a parallel flux is you start out by making a flux. So you'll be using something to take the movie titles and then turn it into a flux of a list of rankings and then turn that into a flux. You'll then convert that flux to a parallel flux. We'll talk about how to do that here shortly. Then you run each of the rails in the parallel flux in the parallel thread pool. We talked about different types of thread pools. There's a parallel thread pool. There's a bounded elastic thread pool. You'll use the parallel thread pool because that's intended for CPU-intensive computations or CPU-bound computations or computation-bound computations. Then what you'll do is you'll only keep the titles that contain the search query, ignoring the case. So this is the query. Once you've got all the movies that are available, you're going to go ahead and only keep the ones that match the query. You'll then convert the parallel flux back to a flux. And then the last thing you'll do is you'll sort the results by title in ascending order, and then you'll return that result as the flux. So that's what search does. Pretty straightforward use of parallel fluxes, not a whole lot of sophisticated stuff here, just a good warm-up. So I would probably start by doing the get all movies method first, followed by search. Now we're getting into stuff that's a lot more interesting. So these are the recommendation methods. And you can see what this is going to do is it's going to take in a single watched movie and a count of how many movies you want that are similar to that movie. And then it's going to go ahead and use the database, the map that we got from the database, in order to find the recommendations. So the first thing that you need to do is this is like one of the very few places, maybe I think there's a couple of places where you you have an if statement or something else that's not in a nice little stream, the first thing you need to do is you need to check that the watched movie exists in the database, in the movie map, which is a projection, an in-memory projection of the database. And if it's not, if somebody says, I would like to see a movie that's similar to something that the database doesn't know anything about, then at that point we return an empty flux. And then once we've got that check out of the way, and that's, again, like one of the few places where we actually have an if statement here, the next thing we're going to do is we're going to create a local flux variable that's initialized using some steps. There's a helper method to get the vector portion of the input movie. There's a method you can use to get the vector portion. And then you'll create a parallel flux stream that contains all the entries in the map. And there's a method down below that can do that for you. So what we're going to do is we're going to get back a stream of all the entries that will run in parallel. And then you're going to go ahead and filter out the watched movie from the flux stream. So we're going to take all the different things and we're going to get rid of the watch movie, because we don't want to have a match come back and say, oh, if you like Star Wars A New Hope, you should watch Star Wars A New Hope. You already know that you like that movie, so we got to get rid of that one. And then we convert the parallel flux back to a flux. And the reason for that is that parallel fluxes have a subset of operations that fluxes do, and we need to do some other stuff on this. And then the last thing we're going to do is we're going to call a helper method that returns the top max count recommendations in the flux of entries. And I'll give you a hint as to where to go find that. That is over here in get top recommendations flux. And there's a couple of different things. You'll have to figure out which one to use. And these are really, really clever. So what they're doing is we come in with a flux of rankings. And what the rankings are is going to be a flux stream of ranking objects that have the movie titles and the results of doing the cosine similarity index computation on that movie compared to every other one. And so what we're going to do now is we're going to basically go ahead and get the top K of these things. So if you've got a stream of this stuff, we want to get the top K, where K is the max count in this case. And there's a super cool method over here. This one is based on get top K. So it uses a heap data structure. And you should actually have, if you remember your data structures class, a heap is a partially ordered, almost complete binary tree. And you can do operations on a heap very quickly without having to sort the entire thing. One way to find out the top K is to sort everything and just pick the top K. That's easy. But that's also somewhat inefficient because we have to do an n log n sort to sort them all. All we want is the top K of them. And so we can use a priority heap to do that, and this is or priority queue, and this is the code that does this. And it's really clever. What it does is it basically builds up this heap as you give it data, and it only keeps the top K elements. And so anytime something else comes along that's higher, the lower one will get evicted, and it just keeps track of the top K. So it takes less time to run than doing a complete sort. Anyway, that's a fun thing to take a look at if you're curious. So you'll need to do those operations in order to take the flux that you computed and get the top K, and then you return that back as a flux. That computation is sequential. There's another get recommendations, which is super clever, and we can thank Sirhi for helping with that, because he helped do it, and it's great. What this does, as you can see, is it takes a list of watched movies, and it goes ahead and comes back with the top max count, top K of them, that are closest matches to the movies in the database. So, for example, if you say, I watched Star Wars and Star Trek and Iron Man or whatever, or Top Gun or whatnot, what'll happen is it'll take all those things into account and it'll compute a sum of cosine similarity scores based on all these other watched movies. So rather than doing it, one at a time, it'll compute the sum and then try to find things that correspond to that sum. There's probably other algorithms to do as well, but this one seemed particularly clever. So what we'll do here is we'll turn the movies map into a flux. We convert the flux to a parallel flux. We'll run the parallel flux on the parallel scheduler. and will filter out the watched movies from the stream, since again, we don't want to say, if you watch Star Wars, Star Trek, and Iron Man, you don't want to be told that those are movies you should watch. And then we'll rank the movies by sum of cosine similarity. And I'll show you where to find those functions in a second. We convert the parallel flux back to a flux, and then we go ahead and return the, make another call to get the top max count recommendation. So again, those are the things you'll be doing there. There's yet another method here called compute recommendations parallel flux. What that does is that takes a given vector for a particular movie, and it converts the movie's map to a flux, converts the flux to a parallel flux, runs the parallel flux in the parallel scheduler, and then it'll call the cosine similarity helper method to create a new ranking object. And so we're going to take a look at those methods. All of those methods are available over here in cosine similarity utils. And I debated having people write these. You can take a look, and there's some implementations that do this stuff. I ultimately decided that this was just pretty basic stuff, and it would not be that interesting to implement. But what it essentially does is it will take two lists of doubles and then decide based on a parameter whether to run them in parallel or not. And if it's in parallel, then it'll turn the list into a parallel stream. Otherwise, it turns it into a stream. Then we go ahead and we multiply each item together, either sequentially or in parallel, and sum them up. So that's the first list. Then we do the same thing for the second list. And then we compute the dot product in parallel if requested. So this is where we come up with the cosine similarity value. We take the dot product and we divide it by the multiplication, the product of the square root of the first vector, first list, and the square root of the second vector or list. And that is what creates the cosine similarity value. Now there's another implementation that Sirhi wrote, which computes the sum of cosines, and it uses that cosine similarity method in order to be able to compute the cosine similarity of each watched movie within the vector, and then it sums all the cosine similarities together. And it does it either in parallel or sequentially, depending on the parameter you pass in. So really cool stuff. Again, if anybody's interested in writing yet other algorithms to do this, let me know, because it's interesting to see what they do. Okay, so that's pretty much the recommendation or the recommenders module. That's the main thing you're going to have to do. Let's take a look at a couple of other things that you'll have to do as well. So something else I mentioned, the database. A lot of this is going to be identical to what you did before. The main difference is going to be that we've added a new method, or two new methods, to the controller called getMoviesMap. And getMoviesMap, as you can see, forwards to the service to get the movies map, and it returns a map that maps strings, which in our case are the titles of the movies, to lists of doubles, which are the cosine similarity vectors. So if we go take a look at getMoviesMap, this is what you have to write, and it's really cool. So what it does is you'll use the repository to get a list of all the movies. You just do a normal call to get the list of all the movies. Then you'll convert that list of all the movies into a stream of all the movies. And then you'll have a collect call, which is the terminal operation that uses a collector, it uses the toMap collector, that collects the results into a tree map. So you'll have to go figure out how to do that. It's not too hard, but what we're basically doing is we're using a tree map, because tree map will keep everything sorted. So the results will be sorted based on the, well, it'll be based on what we do for sorting, which is based on the names of the movies. So you have to write this. And the other thing you have to do here is you have to add the annotation to make this be cacheable, and to be cacheable in the movies cache. Movies cache is a symbolic constant that I define. Hint, super easy, but that's the point. So this is going to be cached. So what that means, as we saw before, is the first time it gets called, it'll compute that movies map, but that movies map doesn't change. So it's a perfectly good candidate for caching. So it'll go ahead and give back that data. It's stored on the server side, and any other subsequent calls that come in for this will just go ahead and return the cached values. So you'll have to write that code, and there's a couple of things that you have to do, but that's basically what you have to do to the database, in addition to adding the stuff you had before. Over on common, the only thing you have to do there is just copy your stuff for the movie class, the entity class. That should all be very familiar by now. I think everybody's doing a good job of that. And then the final piece of the puzzle here is over on the client part. And so what you'll have to do here is you'll have to fill in the HTTP interface mechanisms for the ParallelFlux API. ParallelFlux API is the declarative proxy to that ParallelFlux microservice we saw. And you'll basically have to fill in the proxy methods that will get all the movies, search a movie, do the recommendations for one movie, and do recommendations for all the movies. Again, oh, and then also do the time versions as well. Not particularly hard. As you've seen by now, it's kind of paint by number. Once you know what the controller methods look like, it's easy to do that on the client side. Just make sure that almost all the annotations are the same, except these guys use the at get exchange and at post exchange rather than at get mapping and at post mapping. And I discovered that out the hard way because I mistakenly copied one of the wrong ones over there and my code was blowing up, and it took me a minute to realize that was, of course, a mistake. And you'll notice that we put in the HTTP exchange here so that we'll go to the ParallelFlux. You also have to, in addition to filling in stuff you've done before, the database API will also require you to add a retrofit call that will get back a map. So you'll have to do that small change, not a big change, just a way to get the map back. And then we have the recommender async proxy. This is necessary, this class is necessary because unfortunately HTTP interface does not support dynamic path updates, so you have to kind of do a bit of a workaround here. So the recommender async proxy has an auto-wired ParallelFlux API instance, and then we just write little proxy methods that take a look at the strategy name that's passed in here and the value for timed, and then does the right logic to call the appropriate method on the ParallelFlux API. So just a little bit tedious, but by no means a hard thing to do. So that's the other piece you have to fill in. And then, of course, for all this to work, you have to add in all the, oops, get rid of this. We don't want that. We don't need to have I got rid of the async stuff here because it's unnecessary. In fact, let's get rid of this too, now that I'm looking at it. The async database stuff is not used in this project. And the main thing you have to do here, in addition to copying over your other factor methods, is you have to make a new factor method that will make the ParallelFlux API, which will look very much like the other things you did with HTTP interface. So I think that's basically it. As you can see, there's a lot of pieces, but a lot of this is refinement of what you've done before, the main exception being writing the code to invoke the operations to do the recommendation engine in parallel using ParallelFlux. Now that we've walked through the specification and the skeletons for assignment 3, let's show how to run the unit tests. We go ahead and click on the Gradle tab, and then the Tasks tab, and the Verification tab, and then we double click on Check. And this will go ahead and start to build and run all the tests. There are a large number of tests that are part of assignment 3 because we're testing many of the other pieces you've implemented in the earlier assignments. Not everything, but some of it. As you saw before, we omitted the database EX portions, and we also omitted the various movies portions for assignment 3, but there are a number of tests to run. So those are going to go ahead and instantiate. Now, one of the things to remember while these tests are running, you have to wait a while for them all to finish. And sometimes it's a little bit hard to tell at first glance that the tests aren't done. But the way I typically do it is by looking up here in the upper left-hand part of the screen where it says running tests. And as long as that still is moving around and kind of showing that it's still spinning, if you will, that means that the tests are still running. You can also see down here that the tests are running as well. So if you want to expand these different portions to see what works and what didn't, you can click on the little expander icon. But this will take a while to run. Notice that we've also got some new tests that we added things for example, the ParallelFlux API parts and the various proxies and so on. So after a while, things will go ahead and coalesce. You can also take a look down here in the right-hand bottom corner, which shows that things are still running. Just trying to give you a sense of how you can tell the progress that are being made. But what I typically do is wait for a while, and after a time, we'll see that things are finally starting to coalesce, and as a result, the test will be complete. We have not yet reached that point here, as you can see, and we're up to 75 tests. I think there are actually more than that if we wait a little bit longer. So at some point, everything will be done, and I believe we've reached the end of all the tests. So there should be roughly 83 tests that should pass. And if you run into any problems whatsoever, make sure that you are going to post this to Piazza to get some feedback, and/or come to office hours and talk to Skylar.